Welcome back to AI.Code.Cast listeners. You've thrown us a real brain teaser this time.
Oh, this is a good one.
Finding the smallest missing positive integer in an array. Sounds simple enough, right?
Deceptively simple. The real challenge is doing it efficiently.
Exactly. We're talking linear time, ON.
And to make things even more interesting, constant extra space.
Meaning, we can't just create another massive data structure to help us out. So picture this. We've got this jumbled array, integers all over the place, positive, negative, zero, the whole shebang.
A real mixed bag.
What's our target in this numerical jungle?
We're hunting for the smallest positive integer that's missing from the array.
Okay, so let's say we have an array like 3, 4, next 1, 1.
In that case, the smallest positive integer missing would be 2.
Got it. Seems pretty straightforward. But I'm guessing the solution isn't just a quick sort and search.
You're catching on. Sorting would blow our time complexity out of the water.
Right, most sorting algorithms are at least O(n) log n. Plus, we might need extra space for the sorting process itself.
Exactly, so sorting's off the table.
So we need to get a bit more creative. What if we try to use the array itself as a tool?
Now you're thinking. That's where things get really interesting.
Lead me down this path.
There are a few clever approaches that leverage the array structure, and one that often comes up is the in-place marking technique.
In-place marking. I like the sound of that.
It's all about making the most of the information we already have within the array.
Okay, so we know the array's length, and we're dealing with positive integers. What's the trick here?
Think about the array's indices, the positions of each element. Could we use those to store information?
Interesting. So each index could correspond to a particular positive integer.
Right. But how would we represent whether that integer is present or missing within the array?
That's the tricky part. We need a way to mark an element without needing any additional space. What about using the sign of a number?
Bingo. That's exactly what the in-place marking technique exploits. We can negate a number to indicate that its corresponding positive integer is present in the array.
Okay, I'm starting to see the light here. But before we start marking anything, shouldn't we do a little cleanup? Get rid of anything that's not going to be useful?
Absolutely, a crucial first step. Anything less than 1 or greater than the array's length is just clutter.
So we can replace those with, let's say, the array length plus 1, just to keep things consistent.
Exactly. Now we have a streamlined array, ready for the marking process.
All right, so we've prepped our array, we have our marking strategy. How do we put this in-place marking into action?
Let's break it down step by step. We start by iterating through our cleaned up array. For each number, we take its absolute value.
So if we see the number 3, we'd be looking at index 2.
Right, because we're using zero-based indexing. Now, we check the element at that index. If it's positive, we negate it. That's our mark.
So finding 3, if the element at index 2 is positive, we flip it to negative. That tells us 3 is present somewhere in the array.
Exactly. We repeat this for every number in the array. Of course, we need to be careful about array bounds and all that.
Right, don't want to go messing with memory outside our array. Okay, so we've gone through the whole array. Flipping signs to mark the presence of positive integers. What's the final move?
The beauty of this is the answer is right there in the array. We just scan through it again. The first index where we find a positive element that's our smallest missing positive integer.
So if we see that the element at index 5 is positive, then 6 is our missing number. It's like the positive element is a little flag.
A great way to think about it. And what if we get to the end and we haven't found a single positive element?
That means every element has been negated. So we've seen all the positive integers from 1 to n. The smallest missing one must be n plus 1.
You nail it. There you have it, the in-place marking technique. We found the smallest missing positive integer using only the array itself as our workspace. Linear time, constant space.
Pretty slick. This problem really makes you think differently.
It's all about understanding the constraints and finding a way to make them work for you.
Okay, so we've explored in-place marking. You mentioned earlier there's another approach using cyclic sort. Remind me how that works again.
Cyclic sort is all about getting elements into their correct positions in the array. Imagine you have a deck of cards, numbered from 1 to n. Cyclic sort wants to put card number 1 in the first position, card number 2 in the second, and so on.
Right, sorting those cards into their natural order. How do we apply this card sorting idea to our missing integer problem?
Well, we don't need to perfectly sort the entire array, just the numbers from 1 to n.
So if we find the number 3, we want to make sure it ends up at index 2.
Exactly. Now, if we come across a number that's not in its correct spot, What might we do?
Following the card analogy, we could swap it with a number that should be there.
Good thinking. But we need to be smart about our swaps. We don't want to just create more chaos.
Right. The swap should only happen if it moves us closer to having the numbers from 1 to n in their correct positions.
That's the key. Now think about what we do if we encounter a number that's outside the 1 to n range, or if we hit a duplicate.
Those don't really help us in finding the missing positive integer, so could we just ignore them?
Exactly. Skipping those irrelevant or duplicate numbers is crucial for making this algorithm efficient.
Okay, so we've gone through the array, strategically swapping elements to try and get those numbers 1 to n where they belong. What's next?
Imagine what the array looks like after this. If everything went smoothly, what would tell us a positive integer is missing?
Well, if a number is missing, its corresponding index won't have the right value. Like if 5 is missing, then index 4 won't contain 5.
Precisely. We can go through the array one last time. The first index we find where there's a mismatch, that reveals our missing positive integer.
And what if, somehow, the array is perfectly sorted after our cyclic sort?
Then we know all the numbers from 1 to n are present, and our missing positive integer is simply n plus 1.
Cyclic sort seems very elegant. How does it compare to in-place marking in terms of efficiency?
Both methods achieve that sweet, linear time complexity. They scale really well with larger inputs, but cyclic sort might have a slightly higher constant factor because of the swaps.
So in certain cases, in-place marking might actually be a bit faster in practice.
That's possible, especially when cyclic sort requires a lot of swaps to get everything in order.
So two different but very cool ways to crack this coding puzzle. One uses signs as flag, the other's like shuffling cards till we find the missing one.
And they both hit our target, linear time, and constant space.
Super efficient. Now, I know some of our listeners out there are probably eager to get their hands dirty with some code.
Always love the enthusiasm.
Can you walk us through how we'd represent these algorithms, maybe using some pseudocode? Let's start with the in-place marking.
Sure thing. Pseudocode is a great way to sketch out the logic without getting lost in the syntax of a particular language. For in-place marking, we'd start by looping through the array.
Right. That first pass is where we deal with those irrelevant numbers, the ones outside the 1 to n range. So in pseudocode, we could say, if the current number is less than 1 or greater than the array length, replace it with the array length plus 1.
Perfect. Now we've got an array with only the good stuff, or our placeholder. Next up, the marking step.
Time to flip those signs. If the absolute value of the current number is within the array bounds and the element at that index is positive, negate the element at that index. How's that for pseudocode?
Nice and concise. It really shows how we're using the array itself to store info without needing any extra space.
Okay, so we've got our marked up array. What's the final piece of the pseudocode puzzle?
Now we just need to find that first positive element. So we'd say, if the element at the current index is positive, return the current index plus 1, otherwise continue to the next index.
And if we reach the end of the array without finding a positive element, return the array lengths plus 1. Got to cover all the bases.
Exactly. That sums up the in-place marking algorithm in pseudocode.
All right, now what about cyclic sort? How do we translate that clever swapping into something our listeners can easily code up?
The pseudocode for cyclic sort is all about those strategic swaps. So we begin by looping through the array and checking each element's position.
Right. And if it's not where it belongs, we need to figure out its target location and make the switch.
Precisely. In pseudocode, we might say, while the current element is not in its correct position, calculate its target index, swap the current element with the element at the target index, and update the current element to its new value.
So that while loop keeps swapping until the current element lands in the right spot. And of course, we need to remember those optimizations, skipping over those irrelevant or duplicate numbers.
Absolutely. If the current element is less than 1, greater than the array length, or equal to the element at its target index, skip to the next element.
Smart moves. Once our cyclic sort dance is done, finding the missing integer is just about looking for the first mismatch. Iterate through the array. If the element at the current index does not equal the current index plus 1, return the current index plus 1.
And last but not least, if we reach the end of the array without finding a mismatch, return the array length plus 1.
Perfect. Now we've got pseudocode blueprints for both approaches. It's so cool to see how different methods can lead to the same efficient solution.
Proof that there's often more than one way to skin a cat, or in this case, to solve a coding problem.
Definitely. And for our listeners who are ready to start coding, any common pitfalls they should watch out for?
One thing to be careful of is handling those tricky edge cases. Empty arrays, arrays with only negative numbers, duplicates, make sure your code can handle those scenarios.
Always got to test those edge cases thoroughly.
Another potential gotcha, especially with cyclic sort, is making sure your swapping logic is airtight.
Right. Double check that you're not accidentally overwriting anything or creating an infinite loop.
Attention to detail is key when it comes to these algorithms.
Well, I think we've explored this problem pretty thoroughly. We've discussed two elegant solutions, walked through pseudocode, and even covered some potential pitfalls.
A nice little deep dive into efficient algorithm design.
For sure. And it shows how understanding the constraints can actually lead to more creative and effective solutions.
Couldn't agree more.
We encourage all of you listening to experiment with these algorithms, try different implementations, and maybe even share your insights with the AI.Code.Cast community.
Happy coding, everyone!
And that brings us to the end of another episode of AI.Code.Cast. We hope you enjoyed this deep dive into the first missing positive integer problem. Until next time, keep coding and keep those creative juices flowing.